Hello, everyone. I'm Jo Ashbourne, the director of the St. Cross Centre for the History and Philosophy of Physics, and I'd like to warmly welcome you all to today's special event in association with Oxford's Department of Physics. We've nearly 1,000 people joining us today from all around the world, so good morning, good afternoon, and good evening from across the time zones. We're delighted to welcome Professor Carlo Rovelli to speak on scientific thinking across the centuries and the foundations of physics. Carlo is a professor of theoretical physics at Aix-Marseille University and the founder of the quantum gravity group there. He's also the author of several best-selling books, including 7 Brief Lessons on Physics, which has been translated into 43 languages, as well as his latest popular book, Helgoland. He's been awarded a glittering array of awards and prizes over the years for his pioneering work on quantum gravity. He was named one of the 100 most influential global thinkers in 2019 by Foreign Policy magazine. But perhaps topping all that, Carlo's highest accolade yet just might be that he's appeared as a character alongside Einstein and Mickey Mouse in an Italian Disney comic. Carlo's kindly agreed to take questions after his lecture, and these can be typed into the Zoom chat box at the bottom. Carlo, we're very much looking forward to your lecture. Thank you.
Thank you very much, Jo. It's really an honor and a pleasure, and thanks for mentioning what I consider my greatest achievement, indeed, which is to having appeared with together with Mickey Mouse in a comic Disney strip. Welcome to everybody. I have seen from the chat box that there's people from all over the world. I know that there are many people in. It's a great opportunity for me to give this talk, and I'm particularly happy because this is not going to be sort of my standard talk about physics strictly. I'm not going to talk about quantum gravity. I'm not going to talk about quantum mechanics, specifically about the nature of time, general relativity. I'm going to talk about physics, ideas about physics in general and history of physics in general. Those of you who know anything about my work know that I'm a little bit anomalous as a physicist, precisely because my interest, a strong interest I have, or I've always had, in the philosophy of physics and in the history of physics. I have written a book on an ancient, sort of ancient Greek scientist, I would call Anaximander. I've been teaching a course in history of physics, and I have some papers in some philosophy journals. And in fact, the presentation today will be general, but I will at some point focus on one particular paper that I've written on a philosophy, published in a philosophy journal, which obviously has not been easy to publish, because with all my interest in history of science and the philosophy of science, I'm a scientist. I'm a scientist by formation, by the work that I do in all my life, and so my mind is the mind of a scientist, not of a historian, nor really of a philosopher. And for this reason, I sometimes see things differently. I mean, the discipline from which we come, the culture in which we are, give us different perspective on things, which might make communication difficult with the people who do that professionally, because of course they know, I mean, the people who do philosophy and history of science know much more than me. So what is the scientist coming in and telling things to them? But I do think that when you get a perspective on issues from a new place, something appear which were a little bit more difficult to see from within. And so the paper I will talk about, after having been refereed by 7 referees, with referee reports sometimes 4 or 5 pages long and all sorts of discussions, ended up to be published in a major philosophy journal in America. I'm very proud of it, and I'm going to talk about that, knowing that I'm talking in a field which is not my own, so with all the risks of that. But I want to start large because I'm not just focusing on that specific paper. The argument will be more general, and I'm gonna show some slide. So this is going to be my title. The title actually was suggested by Joe: Scientific Thinking Across Centuries and the Foundation of Physics. It's an extremely large title, and you will see why. Because it is appropriate indeed. Because I will make somehow my entire talk is a point about the history of science and the philosophy of science, with an example, a specific example in which I defend a general perspective. Good. So enough for introduction. Let me go in the business, and let me start from here. I start from my really my own field, which is quantum gravity. I do quantum gravity, which is the attempt, the work, like many other people, to combine the two greatest discoveries in fundamental physics of the 20th century, which are relativity and quantum mechanics. The two, you recognize the two guys here, Albert Einstein and Werner Heisenberg, who is, in my opinion, the person who got the key idea of out of which what we call together today quantum theory emerged. In fact, it's not just my opinion. It's the only one who got the Nobel Prize for the discovery of quantum theory. Now, relativity and quantum theory are called revolutionary, and were immediately called revolutionary because they changed in quite in depth the physics that was considered established at the beginning of the 20th century. And in fact, they arrived as a shock because all through the 19th century, there was a sense that physics had found a definitive description of the world, and that Newton had found some definitive structure of how things are, structure of space, structure of time, structure of dynamics, and the right ways of thinking about that. And it's common in the 19th century to see a view of science that is profoundly cumulative. We discover one thing, we discover another thing, we discover another thing. That's our baggage, that's our knowledge. Relativity quantum theory came as an atomic bomb, not only because an atomic bomb is a result of relativity and quantum theory, but also intellectually, theoretically, because basically one way you have of reading them is that it's the discovery that Newton was wrong, right? So that the Newton equations are wrong. It's strictly wrong. I mean, if you take the basic Newton equations and compute the orbit of Mercury, Mercury doesn't follow those equations. It's a fact. But even more wrong, because the very conceptual structure on which physics was conceived, it's turned upside down, both by relativity and quantum theory. Now, to be more precise, since after all I'm talking also to philosophers and historians, there were strong signs coming just before Einstein and Heisenberg, before relativity and quantum theory. Maxwell and Faraday work at the end of the previous century, and thermodynamics, a number of things were sort of pushing many physicists to the idea that sort of we haven't got it right. There's something to be adjusted, something to be changed. There was idea of rewriting physics in terms of energy instead of matter, various push and pulls. There was a sense of confusion and crisis at the turn of the century, between the 19th and the 20th century, in many people, not in everybody. Some scientists were thinking, we've got the basis, we just have to work out the details. But definitely, when relativity arrived in 1905 and then in 1915, and the two relativity theories, Einstein and quantum theory, arrived in sort of slowly from the beginning of the century, but then the actual theory in 1925, the it was clear that the previous foundations of physics were changed. And so the shock was, okay, so what we learned from science might be wrong. We thought Newton was right and it was wrong. The shock was enormous and motivated the entire reflection of what is the nature of science to restart, in a sense. And it's important to appreciate that, you know, when you go to a science class at the university and they tell you this is the methodology of science, that's the one version of the methodology of science, right? The methodology of science is the Renaissance at the time of Galileo, the time of Newton, at the time of Lagrange, at the time of Faraday and Maxwell, and it has changed. People has changed a lot of what they mean by what they interpret they're doing when they do science. And definitely at the end of the 19th century, there was a sense of science is just an accumulation of facts about the world that was exploded by relativity and quantum theory. And the result in the reflection about science has been varied, but the strongest influence of thinkers about science on the scientists themselves are in the very well-known work of Karl Popper and Thomas Kuhn, who have represented the reaction to the discovery that what we thought was right, Newton theory, etc., actually it was wrong. So we may never know what is right and what is wrong. And Popper and Kuhn are perhaps not the best philosophy of science we have today, because much water has gone under the bridges after Popper and Kuhn, but certainly they have played a huge role in reshaping our understanding of what is science and how it works. And they still are their ideas are still presented in many, at least science classes. I don't know in history, philosophy of science classes, but certainly science classes as this is science. This is what we know science is. And the main idea of Karl Popper is that we have theories, we have data, we have theories. These theories might work for a while, but we never know they're right. And in fact, not only we don't know they're right, but there is no sense in saying that they're right. The only thing we can say about a theory is that it hasn't been proved wrong yet. The main point that Popper emphasizes that you can prove a theory wrong. And in fact, the actual point of Popper is more subtle than that. Karl Popper actually had a more subtle point. What distinguishes scientific thinking for other forms of thinking is exactly the fact of producing theories that can be proven wrong. So for Popper, that's what science is. The kind of thinking that allows you to make a theory, which is a scientific theory, because it can be proven wrong. If you take this literally too seriously, it means that all the theories we have are not proven right. And the only thing we have is tentative theories, which are okay until they're not been proven wrong. Thomas Kuhn was an historian of science, more than a philosopher, but his acute analysis of the progressive development of science and his acute analysis of precisely of the existence of strong breaking points like relativity and quantum theory, which he calls the revolutions, his main book, the Structure of Scientific Revolutions, exactly points out that the development of science goes through these breaking points where everything is redesigned. And of course, clearly both Popper and Kuhn are strongly affected by the explosion of relativity and quantum theory. And they try sort of desperately, I would say, to make sense of science in spite of the fact that the best theory we have, Newton theory, for example, can turn out to be wrong. That was the context. And my point here is the following. Is scientific knowledge truly so non-cumulative as Popper and Kuhn tell us? Certainly we learn something very important from Popper, the importance of falsification. Certainly, we learned something very important from Kuhn, the existence of this breaking point in a progress for scientific knowledge. But is it really true? Like Popper says, that of the theories, we can only say it hasn't been proven wrong yet. And is it really true, as Kuhn teaches us, that, I go back to the previous slide, there is incommensurability between before and after a scientific revolution. Everything is redesigned, even the terms mean something different things. So the previous knowledge becomes, in a sense, obsolete, irrelevant. A century has passed from relativity and quantum theory, and I think we can be a little less under shock for this revolution. We can realize that similar revolution, of course, have all over the history of science, something that Kuhn, of course, discusses in his book, especially in his later books, and that in spite of that, science is far more cumulative than what this picture gives. And there are a number of obvious and less obvious reasons for that, which I want to discuss here before going into my more detailed analysis of the situation. Some are well known, some are less well known, and some are more common, some are, I want to say, are more original. First of all, the quality of a scientific theory come from the fact that it gives a good account of nature in a domain of phenomena. There's no reason we have to judge a scientific theory only on the basis of whether it is universal or not, which immediately tell us that the theories which are abandoned, like Newton's theory, in fact, are very good theory, extraordinarily good theories. Something that, of course, we know very well, because every engineering that builds a house or an airplane or sends a rocket to the moon uses Newton theory. It doesn't use quantum mechanics or Einstein theory. Newton theory is perfectly good. So Newton theory maintains its interest totally, completely, and is still super good science. Okay, so when we know relativity, it's not that we learn that Newton theory is wrong. We just know something more, cumulative. More importantly, second point, we don't want a theory to be certain. We want a theory to be reliable, to work. In other words, we don't want a theory that tell us, oh, for sure the world is like this and like that and like that. Why? Well, because we never had any theory in the history of humankind, because we are creatures, creatures with a small brain, which we can do what we can, and we're not God, who perhaps sees absolute truth. So that's not the name of the game in science. It's not, and that's what distantiate us so much from the 19th century. That's not the game, the name of game in science. Science is a good way for thinking about nature, for understanding it, for making a picture of it, for having a proper conceptual structure, which is reliable. Doesn't have to be final and doesn't have to be certain. We don't want certainty. We never have certainty in life, right? Even the things you're most certain about, you can imagine a case where there is actual possibility that you're wrong for one way or the other. And that's the third point, even stronger and more sharp, what I've been saying. Science is not about the ultimate knowledge. It's about learning more. And I write here, it's about a better organization of our experience. This it's a view of, about science, which is rooted in perhaps in Ernst Mach, who was main philosophical inspiration for both Einstein and Heisenberg at the beginning of both revolutions. Both these men scientists refer to his philosophy as the methodological tool they use for going ahead. And specifically the idea of science of organizational experience as developed by Alexander Bogdanov, which is a Russian thinker, which I think should be studied more. It's not just the empiricism of Locke, Hume, if not Aristotle, that our knowledge is based on experience. Is the fact that our knowledge, and scientific knowledge in particular, is our effort to make sense of all this experience and understand, have a conceptual structure that allows us to to think about reality. Reality is the actual thing which is in front of us, that we understand, we name, we distinguish, we construct with theories. And we want an effective theory. We want a good way of thinking about reality, which fits with reality and fits with experience, which is a completely different idea than, asking what is the Kantian noumenon, the thing in itself, the actual absolute reality. So if you think about science in this way, a little less dramatic than certainty, truth, and thing with capital letters, then you realize that there's a lot of cumulative aspects in science which are completely obvious. And you realize that we should not call mistake what is incompleteness, a step in the way. Now, let me go more specific and use the relation between Newtonian physics and modern physics as an example, right? Newtonian physics is extremely good, and every good student in physics today know how to make the exercise to take quantum mechanics, take general relativity, and show explicitly that the Newton equations are good, the Newton concepts are good, are effective to describe reality in a certain regime. And in fact, knows technically how to characterize this regime. I've written here the three conditions for the regime for Newtonian physics to be good. First, that things don't move too fast, so the velocity is small compared to the velocity of light. Second, that is sufficiently large and big so there are no quantum phenomena, and one can make this precisely. The action in the technical sense of physics involved is large compared to the Planck constant. And third, that the gravitational field is not too strong, and that's again can be put in mathematical terms. And then is actually an exercise which is done in a good course of general relativity. When I teach general relativity, I do this exercise. I have the students do this exercise, and quantum mechanics, to show that the new theories include as a particular case for the regimes, for those regimes, Newtonian physics. Those regimes, of course, is not a special little corner of the of our general theory. It's just the entire regime in which we spend our life, most of our life, except in some particular cases. So that's why Newton theory, it's a good conceptual organization of our experience, which can be ameliorated by enlarging it and including other regimes. Even more subtle is another point, which is completely anti-Kuhnian, in my opinion. And a little knowledge of science, I think, or perhaps a good knowledge of science, shows you how much there is continuity, not just in the phenomena, because the phenomena predicted by Newton theory are also predicted by the relativity of quantum mechanics, but in the conceptual structure. It is true that there is a radical reconceptualization in jumping from one theory to the other through a Kuhnian revolution, but it's just changing one piece of the story when the other 99 pieces are the same as before. And I want to make it particularly strong in the last line I hear. There's one way of writing quantum theory, which is not a Schrödinger way, it's a Heisenberg way, but I think it's conceptually much more clear, where quantum theory is the following theory. If you have a system, whatever system you want, a pendulum, the electric field, the gravitational field, whatever, the quantum theory tells you that to describe the system, you have to use exactly the same variables as a classical theory, exactly the same equations as in classical theory, all of them, plus one. xp minus bx is IH bar, which of course is a dramatic equation because it tells you that the variables are non-commutative with a lot of consequences, which are formal and physical. I mean, this is superposition, quantum interference, laser, atomic bombs, quantum computers, but everything is this extra little equation on a conceptual structure, which is exactly the same as before, right? And Heisenberg invented had the key idea of quantum theory in 25. And then very rapidly, in a few months, the full theory was developed in Göttingen by Max Born, Jordan, and Heisenberg itself. And spectacularly, in parallel, inspired by the first paper by Heisenberg that he got from his advisor, by a young British guy who's Paul Dirac, who got exactly the same theory. And Dirac built the theory on the basis of the formal structure of quantum mechanics, of Hamiltonian quantum mechanics. And he got the same equation, xp minus bx is IH bar, and clarify that that's the key of quantum mechanics. But he got this equation from the Poisson brackets of classical mechanics, so from the formal structure of quantum mechanics. In other words, not only the content of the new theory, of the old theory of Newtonian theory, it's included in the advanced theory, but the entire conceptual structure is carried by. Good. So I want to now to apply this idea to one example where everybody's going to say, no, it's not going to happen there. And the example is Aristotle. Physics does not start with Newton, does not start with Huygens, does not start with Kepler, does not start with Galileo. It starts with Aristotle, who writes a book whose title is Physics, in which there is physics. Okay, and it's a common presentation of Aristotelian. I'm going to talk about Aristotelian physics for a while now. How am I going with time? Okay, good. I'm good in time. It's a common way of presenting Aristotelian physics, to say that is obviously wrong. Is clearly wrong. The guy, Aristotle, was an idiot. He didn't even try to make an experiment and see that his theory was wrong. And by the way, it's completely naive. It's just a sort of what you would do, just opening your eyes and saying trivial things. That's the way Aristotelian physics was presented to me when I studied. I don't know in Oxford what you teach about Aristotelian physics to the kids. Now, I may already notice that it's hard something to be naive and obvious and obviously wrong. I mean, how the two can stay together, it's a little bit complicated. It might be naive and obvious and subtly wrong, but how can it be obviously wrong and naive? I don't know. Now, if you go in the scholarly evaluation of Aristotle, it's all like that. So this common idea of Aristotle is based on the scholarly evaluation of Aristotle. The Stanford Online Encyclopedia of Physics, which is of philosophy, sorry, which is a wonderful source of extremely vast and large. It doesn't even have an entry on Aristotelian physics. I mean, Aristotle, of course, is immense, and all people study Aristotle from all point of view. But it's remarkable that Aristotelian physics is not taken seriously. And this is the best, this quote here from Bolton 95, it's one of the least negative evaluation that I have found in all the literature, in all the scholarly literature about Aristotelian physics. It says traditional scholar has found the notion of congenial, that Aristotle intended method in his work on natural sciences empirical, even if they have criticized him for failures on his count. Namely, to the extent it was what Aristotle was doing was science, it just was a failure. But But he says the current generation has reversed the verdict entirely. The physics in particular, meaning the book physics, is now standardly taken as a paradigm of Aristotle's use of a dialectical method, so not a scientific method, understood largely as conceptual a priori technique, so not based on observation, not based on, empirical methods, getting information from our senses, but a conceptual priori technique of inquiry, which is appropriate for philosophy, so it's obviously not appropriate for science, as opposed to the more empirical inquiries, which we in these days now typically regard as scientific. So in other words, he's saying the physics of Aristotle either is definitely not science, okay? It's just nothing to do with science, it's observation of the world, it's just bad. Or if it is science, as people talked before, it's very bad science because it turned out to be wrong. Okay, now let me give you the vulgate of that, which you find everybody. In fact, everywhere. In fact, you find in textbooks in Italy, in I don't know, in the UK, a high school textbook, or even before, which is that, imagine how stupid is Aristotle. He says that heavy objects fall faster than light objects. Okay, when every kid knows that object falls at the same speed. Right? We all know that objects fall at the same speed. And it's the incredible thing is that Aristotle arrived at saying something like that when it just suffices to try, like Galileo tried, and you see that things fall at the same speed. So Aristotle not only says something which is completely wrong, but he says something that can be disproven by just trying. Okay? It's laughable, completely laughable. That's the common evaluation. I'm a little bit caricaturing it, but it's pretty much a widespread evaluation of Aristotle physics. Now, I'm sure that among serious Aristotle scholars, it's far more nuanced, so I apologize for that. But I wish I could find an actual appreciation of what Aristotle was doing with physics. And let me start from this, okay? Heavy objects fall faster than light objects. And it suffices to try. And immediately you see that Aristotle was wrong. So here's a question to you. Did you ever try? All the teachers that tell that to the students, did they try in class once? Did you ever try to throw out of the window a fork and a piece of paper? Do they fall at the same speed? Of course not, okay? It's obviously wrong that objects fall at the same speed. They don't, okay? Objects fall at different speed. Aristotle is completely right here, okay? So when I realized that as a physicist, I said, wait a minute, what is people saying here? What is so all wrong and so a priori and so incompatible with and what is this immense jump from Aristotelian physics to Galilean Newtonian physics? So I decided to study Aristotelian physics, which is mostly not in the actual physics book itself, is the other book, the Coelho, the Cielo, and Generazione and Corruzione, so scattered through 2 or 3 of Aristotle books. But I'm a physicist. It's not too hard to follow what he's saying and trying to figure out what kind of things he does. So I had some time a few years ago, so I decided to plunge into the study in a way which is which would make a historian scream, namely in a completely anachronistic way, not as an effort to frame Aristotelian physics within Aristotelian way of thinking, but doing the same exercise that we give to our students, which is to derive Newton physics from general relativity, for instance, or from quantum mechanics. Let's say general relativity. So you take a general relativistic point of view, you take the conceptual structure of general relativity, and you see that inside there, you derive exactly the equation of Newton by using a general relativistic perspective, not a Newtonian perspective, obviously, because to connect the two, you need the one which works a little bit better, and you see how it goes to the other in some regime. So here is the point I want to make, and I'll articulate in the remaining time a little bit in details. If you take Einstein theory, general relativity, and you restrict to a particular regime, you go through the equations and you get Newton theory. I want to claim that if you take Newton equations, you find what is a regime Aristotle was talking about, which is where I spend our life, we restrict to that regime, you get exactly Aristotle physics, precisely. Not only that, but the other way around, if you ask where the conceptual structure of general relativity comes from, you see that it's a small modification, ground on the conceptual structure of Newtonian theory. And if you ask where the conceptual structure of Newtonian theory comes from, you see that is a modification, and not even too big, of the conceptual structure of Aristotelian physics. So there is an enormous continuity, completely in the phenomena, and also in the conceptual structure. So knowledge is cumulative, provided that you don't interpret it as, absolute truth, valid in all possible regime, but you interpret it as it is, as an organization of the phenomenon in the regime where we are. But there's continuity not across the few centuries of modern science, but across the 2 millennia of at least Western science, and I haven't done similar exercises with Chinese and Indian philosophy. So let me do an exercise, and I've already used a lot of time, so I'm going to a little bit fast, but I'm going to give you a lecture of Aristotelian physics because it's spectacularly beautiful. It's incredibly beautiful. So this is Aristotelian physics in one slide, and then in the next slide, I'll compare it to Newtonian physics. It is an incredible, beautiful theory, which has remained the dominant theory around the Mediterranean for 20 centuries, not because of dogmatism, of lack of fantasy, of, dominance or whatever, Islamic or Christianity, that's forbidden to think differently, but because it's a good theory. It's an incredibly good theory. So here's the theory. First of all, says Aristotle, of all the kind of changes in the world which are described by different science, different things, we just focus on motion, how things move. And this is something basic on how things move, okay? Great idea, we still use it. Second, we divide motions, how things move, into kinds. Fantastic idea. One we call it violent or unnatural, and one we call it natural. And I'll come back to that. Okay, so that's first conceptual separation. Remarkable idea. Now, what about the unnatural? The unnatural is the motion when there is something causing it. If you throw something, the stone moves, unnatural motion. By itself, it wouldn't move, okay? So it's caused by something else, which you call violent because you have to push, okay? And what happens to violent motion is that there is a cause, it goes for a while, then it exhausts, and then it ceases. Okay? Throw a stone, goes somewhere, and then it ceases. Okay, and then he says, well, okay, that's more complicated. Let's focus on the natural motion. What do things by themselves? If you don't throw anything, if you don't kick anything, if they are not kicked by another stone hitting it. Well, in that case, says Aristotle, says his theory, we have to divide two different theses, the heavens and the earth. Okay, in the heavens, the natural motion of things, this is the picture here, is in circles. Go round and round. Everything goes round circles, or maybe a combination of circles, but the round motion is what gives everything. And now let's come for the one we're most interested about. It is on Earth. So here is on Earth. You see the Earth here. Aristotle says the natural motion is vertical on Earth, either up or down. Okay, and what goes up? What goes down? At which speed? How? For how long? Well, here's the story. All the elements of the Earth can be divided can be thought as being combination of some basic elements, which Aristotle calls earth, water, air, and fire. And then he says these are ordered among themselves. Earth is sort of central, and then there's water, air, and fire. So in the universe, which is, of course, Aristotle knew the Earth is round. He has great pages of science showing what are the convincing arguments that the Earth is round. In fact, the first strong convincing totally convincing argument that the Earth is round. This is Aristotle. Anyway, so the Earth is round, and the Earth as a body is round. It's made mostly by Earth as a substance. Around it, there is a sphere, a shell, which is the natural sphere of water. Around it, there is a natural sphere of air, and around it is a natural sphere of fire. So if you take a body, its natural motion is to go vertically toward its natural place. So a stone, which is mostly based by Earth, goes down in air, goes down in water, and it stops in Earth. Some air goes up in water and stops in air. Fires goes up and so on. And if you have a mixture, for instance, a piece of wood is sort of a mixture of various things, but it's a combination such that it has a part of air such that it's stronger enough to bring it up on water and down on air. So it stops at the boundary between water and air. That's why it floats. Okay? How do they move? This is vertical motion. Well, says Aristotle, it moves at a speed, at a constant speed. So if something falls, it falls at a constant speed. This is what everybody laughs about, because we know from Galileo, it's a constant acceleration. Do we really? We'll come back to that. So it moves a constant speed up and down toward its natural place at a velocity, says Aristotle, that it's given by its mass, but it's also given by the density of the medium in which it is moving. So if the density is higher, the velocity is less. And also, given the mass and the density, it doesn't fix a unique velocity, because velocity still depends on the shape of the body. Very detailed physics, okay? Very detailed physics, very, very detailed. You don't get that a priori. I mean, I challenge anybody to get that a priori. You get that by looking very careful at phenomena, having your students, taking notes and doing very careful things. Good. So let's take that and let's see how it talks to Newtonian physics. Okay? So obviously it's true in a regime. Which regime? Well, the bodies in the sky are just the bodies in the sky. The regime, we see things around us, the moon, the sun, the planet. They obviously go in circles around us, so that's pretty easy. But let's think about the bodies on Earth's surface. The regime is that they're immersed in a fluid because there's air, there's water, okay? It's extraordinarily difficult to take away air, take away water. Even now, we have few places on Earth where we can actually pump away the air, okay? So there's air everywhere. There's water, wine, oil, okay? And so this is, Aristotelian physics is the physics of things that move on the Earth's surface, immersed in a fluid, and of course, being on the Earth's surface in Newtonian terms is subjected to gravity. So I'm a physicist, I know Newton theory, I know how these things move. They move in Newton theory according to the equation. The force is, the acceleration is given by this force. There is a gravity force, there is a floating force, buoyance, this is Newtonian physics, and there is a friction terms. And if something is pushing, there is another external force. So here we are. If there is an external force, as Aristotle say, there is violent motion. If the external force is zero, then we have differential equations. Okay. Newton theory, we know how to deal with this. We solve the differential equation. This is a solution. Okay. So how does the thing move? I plot the solution. There is a short transient phase in which the body accelerates and then very rapidly settle at a velocity, at a constant velocity. So after a rapid transient phase, the body settles at a constant velocity. How long is this transient phase? Let's put the numbers. I do the example. It's too short to be seen. If you throw something in water, if a bird takes a little stone very up in the air, let it go, the stone, most of its fall, it's a constant velocity. If you let something fall into the water or into oil, the velocity is constant. The initial transient phase, it's invisible unless you do Galilean very, very subtle experiments You don't let things fall vertically, but you have them feel on the incline, in which you expand this initial transient phase. But in the entirety of our experience of falling things, we are not in the transient phase. We are not in the Galilean acceleration. We are at constant velocity, exactly like Newton, like Aristotle says. So all these teachers in all the schools of Europe and the kingdom and France and Germany who teach it's sufficient to try and you see Aristotle is wrong, they just say it's nothing totally stupid. It's sufficient to try and you see that Aristotle is right. And all the teachers haven't tried, obviously. Okay. Now let's go more in detail, because here is we have the equation and compare to what is this velocity? Well, as soon as you're outside the phase, the tangent, the hyperbolic tangent here is 1. So the velocity is constant. It depends on the mass. It's bigger for a larger mass. It depends on the density of the water. So it's smaller, this is Amber density, sorry. It's smaller for when the density is larger, exactly like Aristotle say. But even if you have the same mass and the same density, so you have two stones, which is two pieces of something with the same mass, the same density, and you put in the water and you shoot them down, they go down at different speed because of the shape. C is the coefficient that depends on the shape. The friction depends on the shape. So it's exactly all the Aristotelian theory about how things fall. All right, I could go more in detail, but my time is over, so I want to wrap up. So if you take Newtonian physics, you ask what was the domain of phenomena that Aristotle was observing things in air, not in vacuum, obviously, or in water, or in oil, or in wine, or in whatever, on the surface of gravity, not outside, etc. You take Newtonian physics, you do the exercises, and you get a lot of detailed things which are exactly Aristotelian physics. Now, of course, I don't want to say that Aristotelian physics is the same as Galilean physics. I mean, it's not mathematics. It's expressed in non-mathematical form. And I could go long on the list of things that distinguish Aristotelian physics from modern science. They are different because science is cumulative. We learn more things and more methodology. Galileo, no doubt, allowed us. Galileo found a spectacular way for seeing this very subtle initial transient phase where the velocity is not constant, but they accelerate. And how did he do that? Instead of having things falling that they too fast go fast, they're too fast to resolve things, he had them going in an incline, and that expands this transient phase in a way which we can see that before getting to the constant velocity, the velocity actually starts slowly. And if you read his books, it goes on and on and on this start slowly. Is that his discovery? Good. So the relation between Newton physics and Aristotle physics in terms of phenomena is exactly the one as between Einstein theory and Newton theory. It's continuity, but there's much more. Let's talk about the basic element of the concept of structure. And I'm sorry I've used all my time. I don't want to. I'll just say one thing, because that's so basic that I think all the others you can imagine or read my paper. One of the great ideas of Aristotle was to, first of all, to focus on the single motion of things out of all the many changes of the world, right? Flowers blossoming, we aging, night and day, night and day, night and day, my hair becoming gray, all sorts of things that happen in the world. But the idea of just how things move, that you can do a science of that, it's just Aristotelian. We're still working on that. It's much more. The first idea of Aristotle is let's separate a natural motion from a force of motion. Okay? Newton does exactly the same thing. Newtonian theory is based on the idea that you have violent motion, that's subject to a force, F equal ma, the acceleration is given by a force, and natural motion, which is on a straight line. Okay? So it's based on a conceptual idea. And what about Einstein theory? What do bodies do in a gravitational field? Well, again, there's a natural motion, which is a geodesic, and then a forced motion, which is something happening. You may say, yeah, but that's, Aristotle was a little bit silly because he thought that falling was a natural motion. And we know from Newton that is actually a forced motion due to the gravitational force. And in fact, that's how we compute it. Yeah, true. But when you go to Einstein's theory, a falling object, that's following a geodesic. So that's a natural motion again. So in fact, Newton was a short detour from a much better way of viewing things, which is following things are following the natural motion. That's the best way of organizing the phenomena. So I have 2 more slides, very fast. I want to wrap up. First of all, science is cumulative. It's enormously cumulative. Newton understood a number of things, create a number of concepts. Aristotle understood a number of things, created a number of concepts. Slowly, as usual, I've given a bird view picture of the development of dynamics as if the main characters were only Aristotle, Galileo, Newton, Einstein, and Heisenberg. Obviously, the actual working of knowledge has been much more cooperative, and a lot of people has worked in between. It's not just huge jumps, steps, but many little pieces that then at some point get nicely organized together. But this long evolution, which has lasted in the Western science for 2,000 years, has been enormously cumulative. Cumulative in the concept, cumulative in the actual capacity of predictive phenomena, and discarding the past as something incommensurably separate from the knowledge, present knowledge, or considering a theory falsified because we found a phenomena which escaped the theory. It's missing, in my opinion, this cumulative aspect of science, and is due to the disappointment of thinking that forgetting that science it's a progressive thing that builds. Okay, we grow old, we learn more things, Even in learning, at some point, we realize that the simple ideas we got from mom and dad were naive. Well, just wrong, but just badly incomplete, and we learn more. And so does humankind. So if we are less pretentious on the truth content of our theories, if we view the theory a la Bogdanov and Mach as an effective, good organization of our experience, and that's what is reality. The best we can say about it. We recognize this this cumulative aspect of knowledge. We recognize that scientific achievements remain true in the appropriate sense, and that I would say the conceptual refoundation. There's a beautiful metaphor, or simile, which I think Quine loved a lot, and it goes back to Otto, forgot his name, which is that knowledge and scientific knowledge also in particular is like a boat, which is being rebuilt slowly and constantly by changing pieces, but not rebuilt by taking it home, taking it in the shore, in the harbor, and building a new one, but is it rebuilt navigating. So we're still inside the boat of our knowledge, and we keep changing it, adding pieces, making, ameliorating, and sometimes we change something absolutely main must change it, but always within it. So it's the same thing that evolves, and we recognize, it's easy to recognize in the best theories we have today, crucial pieces which were back Greek understanding of natural world 2,000 years ago. And I will close, this is my last slide. The guy who is most responsible for vilifying Aristotle physics is Galileo, my co-citizen, my fellow citizen, Galileo Galilei. If you read his books, it's a lot of insulting Aristotelians, right? In the dialogue, it's a fantastic book of the two maximum systems. One of the characters called Simplicius, and is they pull his legs because he's an Aristotelian, he's a dogmatic, he thinks that things fall at the same speed, and all sorts of other absurdities that Galileo slowly shows are wrong. So in Galileo's book, there is a lot of attack against Aristotle physics, and that's one of the reasons Aristotle physics, it goes back to the Renaissance, one of the reasons Aristotle physics is such bad press, because somehow Galileo convinced everybody that Aristotle physics got everything wrong. But it's pure rhetoric. Galilean science is Aristotelian science. It's completely based on Aristotelian notions. It builds on Aristotle notion. And Galileo himself, in 2 letters that he writes at the end of his life, makes this completely clear. And I will quote these 2 letters. In one, he says, I'm designed. Sorry, I am despised as a despiser, and impunged as an impunger of peripatetic doctrine. Peripatetic is, of course, Aristotelian doctrine. Whereas I claim and surely believe that I observe more religiously the peripatetics, or should I rather say the Aristotelian teachings, namely not the school, but the actual text of Aristotle, than do many that put me down as adverse to them. In other words, I'm building on them, not only in content, but also methodologically. I mean, Aristotle is a master of empiricism, is not an a priori thinker. The book physics is a priori, it's a lot of a priori, but boy, you don't do a physics like that by just closing your eyes. You do physics like that on observation. Nobody has done anything similar for 2,000 years, neither in the Western civilization nor in other civilizations. He had a school around. A lot of people were working for him. And then Galileo also says in another letter, these are all 2 letters he wrote late in his life, I'm sure that if Aristotle returned to Earth, he would accept me among his followers. Careful, he doesn't say Aristotle would follow me, become a Galilean, believe in modern science. No, he says he would accept me, Galileo, the inventor of modern science, as one of his followers on account of my few, but, conclusive, convincing contradiction to him. That's the way science works. Building on past knowledge, picking up what's wrong in past knowledge, what's inappropriate, not wrong, inappropriate for going ahead, and replacing for something more appropriate to go ahead. Thank you. That's my view of science. I've taken a full hour. I am happy to take questions to you. Oh, here is a good question from Afats Mulji. It goes to the core of what I was thinking. It's a short question. Is there a thing as the scientific method? Great question. The answer is yes and no, in my opinion. And in fact, both the yes and no have been articulated in philosophy of science by a number of thinkers. One of the strongest no, famously, is Feyerabend, who wrote an entire book to argue that there is no method in science. While we teach our students in science department that there is a method in science, trials and error, observation, theory, testing the theory, and so on and so forth. So is there a scientific methods? I would say that there are many scientific methods. And the strength of science is existence of these scientific methods, which are tools we've found for ameliorating our knowledge of nature. But the tools themselves are subjected to the same evolution as the knowledge itself. And that's the core, that's one core of how our knowledge grow and science grow. Namely, not only science is not attached to its own unique scientific method. Sorry, not only it's not attached to its own actual discovery, Newton law. It's aware today, particularly after these two revolutions, that we can do better. But even methodologically, a scientist is open to, as Feyerabend would put it, use all the trick possible to discover something. The aim is just, understand better nature, construct better conceptual structure that allows us to make sense of nature and to make prediction, to figure out what is going on, to understand why things happen, and so on. And even the strict verifiability Popperian criterion, which sort of characterize science methodologically, is it so strong? Let me give you an example. It's a question whether the Earth is the center of the universe, a scientific question or not. If you're strictly Popperian, you answer not, right? There's no way of empirically measuring if the Earth is the center of the universe or not. So one, strict empiricists would say that's a philosophical question, has no role in science. But boy, if it had a role in science, right? Otherwise, we would say like Copernicus didn't do anything. The reconceptualization of the world introduced by allowing the Earth not to be a center of the universe has been immensely fruitful and is a scientific advance. Even if the statement that the Earth is center of the universe or is not the center of the universe is not verifiable. So the answer is there are a lot of scientific methods, very good, and the one which we teach our students are good, or effective. We should know them. But the point of science is not to use those methods, is to understand nature. And then, whether the color of the cat doesn't matter. The point is that it catch the mouse. Other question, Michael Omer. So what determines the speed of scientific discovery? And how does proving or existing theory wrong contribute to this? The speed of scientific discovery, it's dramatically slow, right? If you look at the history of science, why it took so long to understand things? Why it took so long to understand relativity? Why it took so long to understand that the Earth is round? I mean, there have been empires, centuries, kingdom, poems, arts, organization, army structures that didn't understand that the Earth is round. I mean, why are humans so stupid? I don't know. It's really because I don't think we are very smart in spite of all our science. Humans are very slow in changing their own mind, and we get attached to conceptualization ideas that work, and we stay with them. And it's definitely hard to try something else. There is a sense around that nowadays science is faster. I think is a perspectival effect. I don't think that we are in a particularly fast period of moving science. Yeah, I mean, 20th century has seen a lot of scientific discoveries, and certainly not only in physics. So as the 19th century, but most centuries have seen. And in fundamental physics, basically what we know is general relativity, standard model quantum mechanics. 1960, 1970. The great recent experimental results, beautiful, black hole, gravitational waves, so on, are all the Higgs are all confirmations of the theories of the 60s and 70s. There are attempts. I'm working on one of these attempts, loop quantum gravity, but science is slow, and it needs to be fed by technology that also advances slow, by new problems. Thermodynamics was prompted by new problems with steam engine and so on, by cultural changes. Quantum mechanics was quite a lot favored by general cultural changes in Europe at the turn of the century. I don't have an answer, but I don't have a recipe for making knowledge go faster either. Aristotle believed, this is Martin Kita, Aristotle believed in a priori thinking. Scientific thinking is based more on logical positive and empiricism. I want to quote this question of this statement because it's Martin who says so. It's certainly a person who is who is learned and who is and that's the kind of things that are often talked at school. In my opinion, they're wrong. They're strongly wrong. Aristotle, or they're wrong. We shouldn't say wrong. They are sort of too partial and misleading. Certainly, Aristotle believed in a priori thinking, right? He uses it repeatedly, but not just in a priori thinking. I mean, you might say that of Plato, perhaps, but or other Greek thinkers before Aristotle, but characterizing Aristotle as somebody who believed Aristotle a priori thinking, I think is to totally miss what Aristotle was doing. Aristotle is at the root of the empiricism of Western knowledge. Just read his biology. It's just an astonishing collection of observations. And sometimes he hides he doesn't talk about the sources of his information like he does in the physics that I've described. But as I said, I challenge everybody to come up with such a detailed, articulated, extremely useful physical theory that just out of pure thinking, not at all. I mean, you don't realize that the speed at which things fall is constant, and it is constant, I insist. And you don't realize exactly the three variables on which it depends, okay? The mass, the density, and the shape, just out of pure thinking. I mean, if you know the theory later on, yeah, you can just have developed an intuition such that, but even people today who know, well, I had to do the calculation with the differential equations with Newton theory to just see, yeah, that's absolutely true. It's Aristotle science, it's mostly observative. And it's remarkable that what is spectacular is that all the observations are actually correct. I mean, the observation biology in his biology are spectacularly deep and vast. And it's remarkable that out of 100 of detailed observations that Aristotle has, there are 2 or 3 errors, 2 or 3 mistakes. And these have been repeatedly pointed out over and over and over and over again. I forgot one. The women and men has a different number of whatever teeth, or which is wrong. Okay, he got one wrong. I mean, Einstein got so many things wrong, many more. But you only hear about the mistakes of Aristotle in empirical observations. And worse, he's blamed of not seeing something obvious, where he actually writes the right things, and is a misunderstanding of Galileo and Newtonian physics to say that things in our experience fall as a constant acceleration. They don't in the limit of what we can measure with the tools that Aristotle had. And the second part, scientific thinking is based more on logical positive and empiricism. Logical positivism, it's a philosophical school coming out from the Vienna Circle, and then grew mostly in America, when, you know, with the war, many intellectuals moved from Europe to the US, or before the war with Nazism, with great names. I mean, Carnap is certainly a major figure, and the others not homogeneous, with some variations, which it's at the root of modern analytical philosophy, and talked so many things to us. But I don't think anybody in philosophy of science today would defend logical positivism or logical empiricism is as the best way of understanding science, for a number of reasons. I mean, for instance, the idea that science is based on facts and observations, and the insistence those times in the 30s and after on the fact that there are pure observations, facts out there, it has completely debunked today, because you don't have pure observation facts. You have whatever you do, you already have a conceptual structure in which you interpret them. And in fact, the more you consider advanced science, the more the observation facts are experiments that require complex machinery, and it requires a full theory to make sense of them. So what is observational fact about the detection of gravitational waves? I mean, what is it? It's a paper published. It's a list of numbers coming out of a computer. What is the thing that moves the antenna? Nobody has seen the antenna moves. There's a huge theory, and this theory, it's based on assumptions. So we have very clear today, I think this is acquired in philosophy of science, that things are far more complicated than just observe, theory, the theory, adapt the theory to the observation, the theory makes prediction, you make an observation, doesn't fit of the theory, you change the theory, and then a new theory. It's far more complicated than that. My interest in the methodology of science and the philosophy of science, it's not independent from my being a scientist. It's obviously the same thing, right? I think a good scientist think about its methodology of science. Great scientists and small scientists, we have to do that, because if we get trapped in the wrong methodology of science, we don't do good science. Einstein spent so much time thinking about what is it to do science, and Bohr and Heisenberg, young Heisenberg, did quantum mechanics because he spent hours and hours talking about Bohr, what it is to do science, and do philosophical conversation about that. So in loop quantum gravity, which is what I think is the best approach to quantum gravity now available, but is not sufficiently confirmed by observation to be convincing to people, to everybody. The underlying philosophy of science is exactly the one I've been describing in this talk. So let me make the connection that you're asking here. If you think that science go ahead in the Kuhnian way by, oh, there's something that doesn't work, throw everything away, pick something new from the sky, okay, totally incommensurable with what is before, okay, and this is a new, okay. Or if you think in the Popperian way, okay, everything is possible until it has been disproven, okay, then you try everything, you try this, you try that, and you say, oh, maybe there are 26 dimensions, maybe there are supersymmetric particles, maybe there is little strings instead of, maybe the Lorentz invariance is violated by quantum gravity. Maybe quantum mechanics is wrong. Maybe all possibilities are open. I don't think that this is the way science goes ahead. I don't think this is what Kepler did, what Newton did, what Maxwell did, what Einstein did, what Heisenberg did. It's the other way around. All these people plunged deeply in the knowledge of the time where it was not sort of working, and believed the knowledge of the time. You see, when Einstein did special relativity, he had Maxwell equations and Galilean, the Newtonian Galilean mechanics, which is invariant and the change of frame. And the two seems not to work. So today, in the Kuhnian Popperian logic, what should he have done? Well, think that, this is wrong or this is wrong and try something else. And no, that's not what he did. He thought that the Maxwell equations were right. Why he thought so? Because they work so well. And he thought that the Galilean invariance change of reference frame, it's also right. Why? Because it works so well. I mean, his father was making power plants with this, and his 300 years of physics worked so well in this environment. So he said, well, these things are so credible, we should find a way to put them together. And he found a way to put it together. So special relativity is a way to have a relative velocity and also the Maxwell equations. That's what it is. Okay. So he jumped ahead by believing in the theory. It's exactly the opposite. A theory that were apparently falsified and apparently in need of a Kuhnian jump in something else. It's exactly the opposite of what he did. And he did the same in some sense with general relativity. And Heisenberg, everybody was trying new equations. Heisenberg changes the notion of what it is to be an electron, keeping the same equations, not changing the equations, right? And adding PQ minus QP, adding something that is then interpreted by Born and Jordan as QP minus PQ. So this is loop quantum gravity. My quantum gravity theory, or the theory of me and my colleagues. General relativity is credible as it is. Quantum mechanics is credible as it is. So forget supersymmetry, forget higher dimensions, forget other parallel universes, forget all the dreams of the theoretical physicists of today. Take these theories in which we have confidence because they work so spectacularly well, just find a way to make them together. And there is a way to make them together. And this is loop quantum gravity. Oh boy. It's what is 6:30 in UK, the 30. My time is over. There are so many questions. I wish I could go them. Apologies for not being able to answer more of them. Thank you very much.
Professor Rovelli, may I just thank you for an absolutely wonderful talk. I have never seen so many and so varied questions in the chat for one of our talks before. People are coming at it with such excitement and such passion. And I think we can absolutely see that across the world, people are wanting to understand the points and the issues that you've made. As a non-scientist, it is hugely interesting and encouraging to me to think about the idea of science being cumulative and scientific achievements remaining true, not needing to throw away the things that we think we might understand, but being able to build on them and take us forward. And I think that came through so strongly in everything that you said. The questions could have taken us off in any different direction. You've said already that you've got another lecture and another talk to give this evening. So on behalf of St. Cross College and our History and Philosophy of Physics series, may I thank you tremendously for all of your efforts this evening. I'm sure that a number of people were asking for suggestions for books and so on, and I would just gently suggest that starting with your own books might be a good place for people to start to understand these things. May I thank Joe Ashbourne, as always, for organising these things, and the Physics Department at Oxford for organising the practicalities for us. But primarily, Professor Rovelli, thank you for giving us your time and exciting and interesting us so much. Thank you very much indeed.
Thank you, Carl. Thank you very much. It has been a real pleasure.